And now let us quickly run through an example of a comprehensive application of IEC 61499 for designing a flexible automation system. But we'll take a very simple example for that to see all the tricks and the benefits of IEC 61419 design in one hand, but also we'll keep it very simple. So as a running example, we take this flasher. The flasher is a simple product, let's say imaginary product that has 4 running lights, like Christmas lights, which run from one direction to another, or backwards, of the lights flashing together, or they counting up like a binary number. So some implement some functions that may be interesting to have. And in addition to the lights, it has also some switches to start and stop, a button to select the mode in which the lights flash, the switch, and to select the frequency with the lights flash. Also, we have another switch. And all these devices, all the lights and all the buttons, we will connect to a small PLC that is 61499 compliant, and then we will see how we should write a program to implement this system in the most interesting and useful way. So the operation of the system will look as follows. That's a computer simulation of the flasher product that has, you see, start and stop buttons. It has the this red color knob to change the frequency of the flashing, and also it has the switch, this menu, drop-down menu on the right hand side to change the mode of flashing on the fly. You see that now it's counting up, and now it will be counting down. So, such a simple product. What is 61499 implementation of that? An implementation is this network of function blocks. So this implementation is built following so-called object-oriented principle, where all devices that are components of our product, such as start and stop button, or the selector of frequency, or the drop-down switch for operating mode, they all are implemented with separate software components, like objects. So this software component mode is a function block implementing the drop-down menu for selecting the operating mode. And the result of this selection is an integer number I, the output of this function block, that is passed to the flash gen function block that is generating the array of numbers that are actually representing the lights. And the lights themselves are implemented with the function block LDHMI. So this function block receives the array of numbers, the 4 numbers, which are Boolean 0, 1 values, and just displays them on the lights. And because this flasher, the flash gen block, gets activated by event rec periodically, and that is ensured by the periodic function block of type eCycle, that with a given frequency keeps sending events through its EO output to the flash gen input rec. So the array of values gets updated at every invocation of this function block, at every event arrived. So with a given frequency, it will be creating here at the output new array of values and will be emitting event CNF. And with event CNF, it will be requesting the LEDs block to refresh the picture. So, and how does the periodic block know what is a frequency? It's an input that is coming from the selector, from this in-time function block that is responsible for implementing the frequency selector. So it will emit event every time that the frequency value has changed and will provide the updated value of frequency as its output out. And that will go to be the input of the e-cycle function block. And this e-switch function block is a Boolean switch that selects between two output events, EO0 and EO1. EO0 used to stop the operation, and EO1 is used to start the operation of this periodic block. So, and these are coming as the output of the start-stop button. So, when we press the start button, here will be the event, and here at the value at output out there will be value 1, and as a result EO0 EO1 event will be emitted and the start of the e-cycle will take place. So this is the overall structure. It's very much object-oriented, and the central functionality of this block is implemented in this flasher 4 function block type that internally is seen as an execution control chart of it is shown here. So it's kind of daisy structure of the execution control chart where every state here in among those 6 states corresponds to one of the modes of operations or the initialization. So for each of the modes, count up, count down, chase up, chase down, and flash all, there is one dedicated state. So if the mode is equal, let's say, to 1, every time the block is activated by event rec, this block will jump to this state count up, will execute algorithm count up, and emit CNF event. And the algorithm count up has to produce the next array of values to be displayed. So this is how this function block works. Okay, so now having designed this function block application this way, we can immediately test it by running it on a computer, as you have seen. And after making sure that we achieve the desired behavior, we can deploy the very same function block network, not to soft PLC, but to a real PLC that is compliant with IEC 61499 standard. So, and moreover, with such implementation, which is component-based, we could easily change the deployment of our function blocks from one single PLC to have it in several networking devices. For example, we can imagine a modification of our product so that every of those end devices is now a smart device that is connected via network to a CPU, and we would deploy the flasher for functionality definition into the CPU, but all other function blocks we will deploy in their respective microcontrollers of their respective smart devices. And suddenly this function block application will become distributed across several devices. Still, they will be running as if it was one program. Okay, so that it explains why it is beneficial to model functionalities in such a hardware-independent way, because the devices may come from different vendors. And with such design, same function block diagram can be executed on different types of controllers or on different hardware architecture. Alright, so and to illustrate a little bit this idea, we will see how we could modify our initial Flasher application to extend the physical system with more end devices. So there could be many opportunities of extensions, like adding additional buttons for changing the frequency, or adding a mobile phone based buttons, for example, or adding a display that is displaying frequency, or adding extra arrays of lights so that the lights will be running not along 4 but along 8, and then making circle, for example. So it's different extensions can be imagined, and we'll just see how we do that. So for example, if we wanted to extend our system with one extra array of lights, and we add a couple of buttons that will be also controlling the frequency in parallel with that existed frequency knob, and also we want to extend that with an indicator displaying the current frequency. So the topology of the distributed system could look, for example, as follows. So we could have the main block of switches in one device, and then another block of switches in another block of switches, plus one array of LEDs in another device, and one more array of LEDs in the third device. So we will have 3 devices, and the information flow between the devices could be looking as follows in this picture. So let's take our original function block diagram. So that's almost same function block diagram as you've seen before for the Flasher application, where one function block corresponds to one of these end devices, and then we just add more devices and add more function blocks. So you see that we extended the array of lights with 4 more lights. So for that purpose we need to add more of the logic, this flash 4 function block. So we just provided yet another instance of that, and we connected them so that they will be passing lights from one to another. So we will have one more display block for LEDs. Then for this new indicator, we added a corresponding function block that will take the frequency from the frequency generator, and will also take it as an input and will display it there. So the frequency value will go to the e-cycle as in the previous application, but will also go to the display of frequency. And these 2 new buttons, which will implement like up and down of frequency, so they will also come to the function block that will take the frequency from the knob and then provide additional means to decrease or increase it by just receiving the corresponding events. So here is a new topology of function block, new application that implements the extension of the functionality. And you see that we didn't touch the previous application. We just extended it with new features in a pretty easy way. So that is the way how it is supposed to be in IEC 61499. So the technology is supposed to be very helpful in modifying systems during its lifetime, following the object-oriented concept. Thank you very much.